All right, so welcome to the lesson on parametric equations and vectors. So the big question that you might be asking is, what is a parametric equation and why do we need them? So back in the fall, let me back up for a second. We're going to be using parametric equations and vectors to describe mostly motion. And we've talked about motion back in the fall, but back in the fall, when we had a velocity equation, it was in terms of t. And so what this described was a straight line motion either to the left or to the right. And so we could describe the path or motion of a particle at any particular time as long as it was along that horizontal path or a vertical path. Now, the problem comes in that most objects do not follow along a horizontal or vertical path, so we need a way to describe motion. And what a vector is a way of describing motion both horizontally and vertically. It has a direction component to it as well as a magnitude component to it. Well, you may think, well, the velocity equation right here has a direction component to it, and that is true somewhat. If the velocity was positive, that meant it was moving either to the right or moving up. And if the velocity was negative, that means that it was moving to the left or it was moving down. But what if you have, for example, a bug that lands on your screen right here, and it lands and then starts walking around on your screen? Well, the motion of that bug is not going to be in a linear motion. It's not just going to walk along an x-axis or a y-axis. And so we need a way of describing the motion and path of that object or particle, okay? And what we can do is, with the parametric equations, you are going to be describing the motion both horizontally, which is x of t, and the horizontal, you're going to have a horizontal function in terms of time, and also y of t, which is going to be a y equation in terms of time. So we can describe the motion both horizontally and vertically to describe any particular point on a plane that the particle is and at what time it got there. All right, so let's take a look at a sample equation or a sample problem here. It says make a table of values and sketch the curve indicating the direction of your graph, and then we're going to eliminate the parameter. Now, the parameter in this case is going to be t, which we're going to refer to as time most of the time. Does not have to be t. It can be any kind of parameter that you want, but since we're going to be talking mainly about motion, we're going to use t for our purposes here. So the first thing is we need to make a table using various values of t, including negative numbers, positive numbers, and 0 to get a representative number of points here. So when x is negative 2, you can put negative 2, when t is negative 2, you're going to put negative 2 in for t, so that gives you negative 4 minus 1, which is negative 5. Putting negative 1 in for t, you're going to get negative 3. Putting 0 in for t, you get a negative 1. Putting 1 in, you get a 1, and then a 3, and a 5. All right, so now we're going to substitute those same t values into the y equation. So when t is negative 2, you're going to get a y value of 3. When t is negative 1, you get a y value of 2. T is 0, you get 1, 0, negative 1, and then negative 2. All right, so if we plot these points on an xy coordinate plane, -5, 3 is located right up here. -3, 2 is located right here. -1, 1, 1, 0, 3, -1, and then 5, -2. And you can see that all of these points are on the same line. And you say, well, why can't we just write the equation of that line in terms of x and y? Well, you could, except that would not tell you at what time the particle was at each of these points. An equation with dy dx does not give you a starting point, does not give you an ending point, does not tell you when the particle was at the different coordinates. All it does is give you the direction of your particle, and that's all it gives you. Now, could we write an equation for this line in terms of x and y? Yes, we could. And what we do is a process called eliminating the parameter. So to eliminate the parameter, you're going to solve one of your equations for t. All right, so we're going to take x equals 2t minus 1. We're going to solve for t. So that's going to give you x plus 1 is equal to 2t, or t is equal to x plus 1 over 2, which is the same thing as 1/2 x plus 1/2. Now we're going to substitute this into the other equation in place of t. All right, so that's going to give us y is equal to 1 minus this 1/2 x plus 1/2, which is 1 minus 1/2 x minus 1/2, or -1/2 x plus 1/2, which is a line. This is your y-intercept, which we can see here is 1/2, and -1/2 is your slope, so you can see that yes, we are going down 1 and over 2 for our slope, down 1 over 2. And so this would generate the same graph in terms of x and y, but by eliminating the parameter, we don't know at what time the particle was at each of these points along this graph. It just gives us the location. All right, so we're going to take a look at derivatives, and we're going to be seeing a lot of formulas here. The first one is your derivative dy dx. Now, dy dx is equal to dy dt over dx dt. And the reason being is because if you think of this as a division symbol, if you take dy dt and divide it by dx dt, well, when you divide by a fraction, you multiply by its reciprocal, and the dt's would cancel, which gives you dy dx. All right, so this is your method of getting dy dx when you have parametric equations, one in terms of y with respect to t and the other in terms of x with respect to t. And then the second derivative is going to be this formula here. So what we have to do for a second derivative is take the derivative of dy dx. Now this is your derivative of dy dx. Now what this is going to give us is some equation in terms of t, because this, for example, would be an equation in terms of t. This would be an equation in terms of t. And so that means dy dx is going to be in terms of t. It's going to have a t variable in here, in other words. All right, so when we take the derivative of dy dx, you're going to end up with a derivative with respect to t of dy dx But then chain rule says we have to multiply by the derivative of the inside part. And the derivative of the inside part would be times dt dx, because t was our variable on the inside there. All right, so now when you multiply by dt dx, that would be the same thing as dividing by dx dt. All right, so you're going to take the derivative of dy dx, which is what you end up with up here. Take the derivative of this, which would possibly involve your quotient rule. And then you're going to divide that by dx dt, which is just the derivative of your original x component. All right, so when we see x prime of t, that means the same thing as dx dt, which is the rate at which the x coordinate is changing in the horizontal direction. All right, so we're going to be seeing the rate at which the particle changes in the horizontal direction, and dy dt is the rate at which the particle changes in the vertical direction. All right, so now we're going to have some vectors. The vector notation is this angled bracket right here. That indicates a vector. And vectors have magnitude and direction, and we'll see a little bit more what that means here in a minute. But your vector is going to have an x component in terms of t and a y component in terms of t. There are three different types of vectors that we can have: position, velocity, and acceleration, or at least these are the ones we're going to discuss. So your position vector is going to be x of t, y of t. Your velocity vector is going to be x prime of t, y prime of t. And your acceleration vector is x double prime of t, y double prime of t. So it's very much like what we discussed in the fall with your motion, where velocity is the derivative of position and acceleration is the derivative of velocity, or the second derivative of position. So these we've talked about before. These are just your first and second derivatives. This formula right here is the speed of the particle, or in other words, it is going to be the magnitude of the velocity vector. Now, vectors, you can think, well, what is a vector? Well, if we have a vector, it has magnitude and direction. So what that means is that if you have this vector right here, a vector is going to have a starting point at our origin. The arrow indicates the direction which the object is moving, and then the magnitude, which is going to be the speed of the particle in this situation, would be the length of this vector. Now, this arrow is not like a ray from geometry. This arrow does not mean this is a ray that keeps on going forever. The arrow just indicates the direction that we are moving, and it is stopping right here because the magnitude is going to be the length of this vector. Well, how do you find that? Well, if you have a velocity vector, that means you're going to have x prime of t here and y prime of t here. And Pythagorean theorem, you would have this squared plus this squared equals this squared, which means the length of this side would be the square root of the sum of these two sides squared, which is our formula right here. So when you see this square root of dx dt squared plus dy dt squared, that's really just Pythagorean theorem is all it is from right here. It just gives us the length of this velocity vector. Again, the velocity vector has a velocity in the horizontal direction and a velocity in the vertical direction. All right, so then we have our next formula, which is similar to this one, The difference is we are doing an integral from a to b of this square root. And what that gives us is the length of the arc of our parametric equation. And the difference is going to be this one has a integral, whereas this one does not. And you can refer back to the previous video that we had on arc length when we were dealing with just equations in terms of x and y to see how we got this equation here. And back in that one, when it's an equation in terms of just x and y, this was 1 plus dy dx squared. But when we have a horizontal and a vertical component, we're going to have dx dt squared plus dy dt squared right here. All right, so let's take a look at this example. It says a particle moves in the xy plane so that at any time t, the position of the particle is given by x of t is equal to t cubed plus 4t squared, and y of t is equal to t to the fourth minus t cubed. So part A is asking us to find the velocity vector when t is equal to 1. So the velocity vector, just your formula, was x prime of t, comma, y prime of t. But then we're going to evaluate this when t is equal to 1. So our derivative of x of t will be 3t squared plus 8t, and then y prime of t is 4t cubed minus 3t squared, evaluated when t is equal to 1, which will give us the velocity vector 11, 1. Now, if we were to graph our velocity vector, 11, 1 would be located over here, 11 to the right and up 1. That would be what the velocity vector would look like. Now, part 2 says to find the acceleration vector when t is equal to 2. All right, so your acceleration vector is going to be the second derivative. So the second derivative will be 6t plus 8, and then 12t squared minus 6t, evaluated when t is equal to 2. All right, so that's going to give us 20, 36. And that would be our our acceleration vector when t is equal to 2. All right, I'm going to go ahead and stop this for the first set of videos on the parametric equations, and then I'll set up and record part 2 here in a minute.